Zara Thorne stepped off the military transport bus at Blackwater Naval Air Station with a canvas toolkit that looked like it had survived 3 wars and a duffel bag held together with duct tape. The Pacific Northwest rain hammered the tarmac as she gazed up at the sleek fighter jets lined up like steel predators against the stormy sky. This was it, the most advanced aviation maintenance facility in the world, where only the elite worked on aircraft worth more than small countries' GDP. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The other new recruits strutted past her with their pristine titanium toolboxes on wheels, each one loaded with the latest computerized diagnostic equipment that cost more than most people's cars. Their uniforms were crisp, their boots mirror-polished, and their confidence radiated the kind of entitlement that came with graduating top of their class from prestigious technical academies. Zara's own tools rattled in their worn canvas roll, a collection of seemingly ancient implements that her grandfather had passed down through 3 generations of aircraft mechanics. The handles were worn smooth by decades of use, the metal darkened with age and honest work. To anyone looking, they appeared hopelessly outdated in an era of precision laser measurements and computer-guided assembly. Chief Petty Officer Maksim Vega stood at the entrance to Hangar 7, watching the new maintenance recruits file through the security checkpoint. His weathered face had seen everything the Navy could throw at him over 25 years of service, but he still took pride in sizing up fresh talent. Today's batch looked promising, young, eager, and equipped with the kind of cutting-edge tools that made his job easier. Then he saw Zara Thorne. She moved differently than the others, with a quiet confidence that came from experience rather than education. While the other recruits clustered together, comparing their expensive equipment and swapping stories about their technical school achievements, Zara walked alone, her eyes already studying the aircraft visible through the hangars. Massive doors. "Torres!" Vega called to his second-in-command, Petty Officer Nina Torres. "What's the story on the one with the museum pieces?" Torres consulted her tablet, scrolling through personnel files. Thorne, Zara, 28 years old, no formal aviation training, worked private sector for 8 years, crop dusters, charter flights, bush planes in Alaska. Scored perfect on the mechanical aptitude tests, but her background check shows she's been working on aircraft older than some of our instructors. Vega frowned. The Navy's elite maintenance program typically recruited from top-tier technical schools, not backwoods airstrips. How'd she even qualify for this assignment? "Emergency personnel shortage," Torres replied. "They're pulling from unconventional sources. Her references are solid, though. Former employers describe her as gifted and intuitive with mechanical systems." As if sensing their scrutiny, Zara looked up and made brief eye contact with Vega. He saw something in her gaze that reminded him of the old-school mechanics he'd worked with early in his career, the ones who could diagnose an engine problem by sound alone and fix complex issues with nothing but basic tools and decades of experience. The orientation began in the briefing room, where Commander Elena Rostova outlined the program's expectations. The Blackwater Naval Air Station was home to the Navy's newest fighter jets, the F-35C Lightning II variants that represented the pinnacle of military aviation technology. Each aircraft cost $50 million and contained systems so sophisticated that their maintenance required constant updates to keep pace with evolving software and hardware. "Ladies and gentlemen," Commander Rostova announced, her voice carrying the authority of someone who had climbed the ranks in a male-dominated field, "you are here because you represent the best mechanical minds the Navy can find. These aircraft are not just machines. They are strategic assets that can determine the outcome of conflicts. When pilots trust their lives to these jets, they are trusting your expertise." She gestured to a massive display screen showing cutaway diagrams of the F-35's internal systems. Modern fighter aircraft contain over 6 million lines of code, more than a commercial airliner. They have stealth capabilities that depend on precise tolerances measured in fractions of millimeters. A single misaligned panel can compromise a mission and endanger lives. Zara listened intently, but her eyes kept drifting to the hangar beyond the briefing room windows. Through the glass, she could see mechanics in coveralls working on aircraft that looked more like spaceships than anything she'd encountered in her rural Alaskan experience. The technology gap was intimidating, but something about the fundamental shapes and purposes felt familiar. During the lunch break, the other recruits gathered around Bradley Castellano, a 22-year-old graduate from the Naval Aviation Technical Institute who had arrived with a toolkit that looked like it belonged in a space program. His diagnostic equipment could interface wirelessly with aircraft computers, providing real-time analysis of systems that Zara had never heard of. The key to modern aviation maintenance, Bradley explained to his growing audience, is integration with digital systems. These old-school approaches are obsolete. Everything now is computer-controlled, sensor-monitored, and digitally diagnosed. You can't fix a modern fighter jet with a wrench and some intuition. He glanced meaningfully at Zara's canvas toolkit, which sat alone at a nearby table. Some people haven't gotten the memo that we're not working on World War II prop planes anymore. The comment drew chuckles from several recruits, but Zara remained focused on her meal. She'd heard similar dismissals throughout her career, usually from people who mistook complexity for sophistication and assumed that newer always meant better. After lunch, Chief Vega led them into Hangar 7 for their first hands-on assessment. The space was cathedral-like in its dimensions, filled with the sleek forms of F-35C Lightning II fighters in various stages of maintenance. The aircraft seemed to absorb light, their stealth coatings giving them an otherworldly appearance that made conventional aircraft look primitive by comparison. Your first exercise, Vega announced, is diagnostic evaluation. Each team will be assigned an aircraft with a simulated malfunction. You have 2 hours to identify the problem and propose a solution. This is not about speed, it's about accuracy and methodology. Zara found herself partnered with Petty Officer Second Class Carmen Reeves, a veteran mechanic who had been working on Navy aircraft for 6 years. Reeves took one look at Zara's ancient tools and barely suppressed a sigh. "Look," Reeves said diplomatically, "I know you're probably good at what you do, but these birds are different. Maybe you should observe today and get familiar with the systems before jumping in." Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Their assigned aircraft was Fighter 47, an F-35C that had been flagged for mysterious electrical irregularities during flight tests. The official diagnostic computers showed intermittent system warnings that didn't correlate with any specific component failures. 3 previous maintenance teams had replaced various electrical modules, but the problems persisted. Zara approached the aircraft slowly, running her hands along the fuselage and studying the access panels, while Reeves connected her laptop to the fighter's diagnostic port and began downloading error codes. Zara pulled out a small handheld device that looked like it had been built in the 1970s. "What is that thing?" Reeves asked, pausing her computer analysis. "Electromagnetic field detector," Zara replied, moving the device systematically around the aircraft's external surfaces. "My grandfather built it for troubleshooting radio interference in old aircraft. Still works better than most modern equipment for certain types of problems." Reeves watched skeptically as Zara traced seemingly random patterns around the fighter jet, occasionally stopping to make notes in a leather-bound notebook that was as worn as her tools. The contrast between Reeves's sleek laptop displaying cascading data streams, and Zara's primitive-looking equipment was almost comical. Meanwhile, other teams had begun their assessments with impressive displays of technological sophistication. Bradley's team had deployed a mobile diagnostic station that looked like mission control, complete with multiple screens showing three-dimensional system analyses and real-time component status updates. The beauty of modern diagnostics, Bradley explained loudly enough for nearby teams to hear, is that the aircraft essentially tells you what's wrong. The onboard computers monitor thousands of parameters continuously and can predict failures before they occur. His teammate, Rebecca Manning, nodded enthusiastically. It's like having the aircraft's entire medical history available instantly. We can see not just what's failing, but why it's failing and when it started failing. Across the hangar, Zara continued her methodical examination with tools that predated most of the technology surrounding her. She had removed several access panels and was using what appeared to be a modified stethoscope to listen to various components, while the aircraft's systems cycled through startup sequences. "Finding anything?" Reeves asked, genuinely curious. Despite her initial skepticism, "Maybe," Zara replied, making another note. "There's an interference pattern that doesn't match the electrical layout shown in the technical manuals. It's subtle, but it suggests that something is creating electromagnetic noise that the shielding isn't designed to handle." The diagnostic computer would detect electromagnetic interference, Reeves pointed out. "That's basic functionality." Zara looked up from her notebook. "Would it detect interference that's within normal parameters individually, but creates problems when multiple systems interact? Something that looks like separate small issues rather than one large problem?" Before Reeves could answer, Chief Vega's voice boomed across the hangar. "Time! All teams report your findings." One by one, the teams presented their analyses. Most had identified various potential component failures and recommended replacement of specific modules. Bradley's team had produced an impressive presentation, complete with probability matrices and predictive failure analysis, concluding that the aircraft needed updates to its flight management software and replacement of 2 electrical control units. When Vega reached Zara's team, Reeves stepped forward to deliver their report. "Sir, we've identified a potential electromagnetic interference issue that may be causing cascading system conflicts. The interference appears to be coming from an unexpected interaction between the aircraft's own systems rather than an external source." Vega studied their minimal notes compared to the comprehensive reports from other teams. "And your recommended solution?" Zara spoke for the first time during the presentations. "Sir, before recommending expensive component replacements, I'd suggest checking the grounding pathways in the aft electrical bay. If I'm right, there's a grounding wire that's made contact with a structural support in a way that creates an antenna effect. It would be intermittent based on vibration and temperature, which matches the reported failure pattern." The hangar fell silent. Bradley snorted audibly. "That's impossible. These aircraft have redundant grounding systems with multiple fail-safes. The diagnostic computers would detect a grounding issue immediately." "Would they?" Zara asked quietly. "If the grounding fault is intermittent and only occurs under specific conditions, and if it's not affecting any single system enough to trigger warnings, would the computers recognize it as a pattern rather than random electrical noise?" Commander Rostova, who had been observing the presentations, stepped forward. "Explain your reasoning, Thorne." Zara opened her worn notebook to a page covered with hand-drawn diagrams and calculations. "The electromagnetic signature I detected suggests that electrical current is taking an unintended path through the aircraft structure. This creates a variable antenna that interferes with multiple systems simultaneously, but at levels below their individual warning thresholds." She traced a finger along one of her diagrams. It's like having a conversation in a room where everyone is whispering different things at the same time. No single voice is loud enough to be clearly disruptive, but together they create noise that makes communication difficult. "And you think this is caused by a single misplaced grounding wire?" Commander Rostova asked. "Sir, in my experience, complex problems often have simple causes. The more sophisticated a system becomes, the more ways small irregularities can cascade into larger issues. Sometimes you need to step back from the digital analysis and use more basic investigative methods." Bradley couldn't contain himself any longer. "Commander, with respect, this is exactly the kind of outdated thinking that wastes time and resources. We have sophisticated diagnostic systems specifically because intuition and guesswork aren't reliable. The computers have already ruled out simple grounding issues." Commander Rostova considered both perspectives. "Very well. Tomorrow we'll test these theories. Bradley's team will implement their recommended software updates and component replacements. Thorne's team will investigate the grounding issue. We'll see which approach solves the problem." As the teams dispersed, Zara could hear the whispered conversations starting around her. Words like amateur and lucky guess followed her as she packed up her vintage tools. Carmen Reeves walked beside her, clearly torn between professional skepticism and curiosity. "You really think it's that simple?" Reeves asked. "Simple and easy aren't the same thing," Zara replied. "Finding the right grounding wire in a $50 million fighter jet is like finding a specific grain of sand on a beach. But sometimes the old ways of looking can see things that new ways miss." That evening in the barracks, Zara found herself isolated while the other recruits gathered around Bradley to discuss advanced diagnostic techniques and the latest innovations in aviation technology. Their conversation was filled with technical jargon and confident predictions about the future of aircraft maintenance. "The thing about traditional mechanics," Bradley said, his voice carrying easily across the room, "is that they refuse to adapt to modern realities. They're stuck in the past, trying to apply obsolete methods to advanced systems they don't really understand." "But what if she's right?" asked Rebecca Manning, though her tone suggested she found this unlikely. "She won't be," Bradley replied confidently. "The diagnostic computers on these aircraft represent millions of dollars of development and testing. They don't miss simple grounding issues. If there was a basic electrical fault, the system would have identified it immediately." Zara lay on her bunk, studying technical manuals by the light of a small reading lamp. The schematics for the F-35C were incredibly complex, but as she traced the electrical pathways with her finger, she began to see patterns that reminded her of simpler aircraft she'd worked on. The fundamental principles remained the same, even if the implementation had become vastly more sophisticated. Her notebook lay open beside her, filled with observations and calculations that would have looked primitive to her fellow recruits. But Zara had learned long ago that understanding came not from the sophistication of your tools, but from the depth of your observation and the patience to see connections that others missed. Outside, the Pacific Northwest rain continued to fall on the rows of fighter jets that represented the pinnacle of human engineering achievement. Tomorrow would determine whether decades of experience with simple aircraft could compete with the latest innovations in aviation technology. The next morning brought crisp, clear weather that revealed Blackwater Naval Air Station in all its imposing grandeur. Fighter jets gleamed on the tarmac like works of art, their stealth surfaces catching the early sunlight in ways that seemed to bend physics itself. Chief Vega had assembled both teams in Hangar 7 by 0600 hours, determined to resolve the diagnostic challenge efficiently. Fighter 47 sat in the center of the workspace, surrounded by the tools and equipment that would put two completely different approaches to mechanical problem-solving to the test. Bradley's team had arrived early to set up their sophisticated diagnostic array. Multiple laptops displayed real-time system analyses, while tablet computers showed three-dimensional models of the aircraft's internal components. The mobile diagnostic station looked like something from a science fiction movie, complete with wireless sensors that could monitor dozens of parameters simultaneously. "The beauty of our approach," Bradley explained to the gathered observers, "is efficiency. Instead of spending hours crawling around looking for problems, we let the aircraft's own computers guide us to the exact issues. It's faster, more accurate, and reduces the chance of human error." See, his teammate Rebecca had already begun downloading updated software modules while their diagnostic computers ran comprehensive system checks. Their methodology was impressive in its technological sophistication and systematic approach to problem solving. Meanwhile, Zara had quietly begun her investigation in the aft electrical bay, armed with her grandfather's electromagnetic detector and a small mirror mounted on an adjustable arm. Carmen Reeves watched nervously as Zara squeezed into spaces that seemed too small for human access, following wire harnesses with the patience of an archaeologist uncovering ancient artifacts. "This is taking forever," Reeves muttered, checking her watch. "Bradley's team has already identified 3 potential software conflicts and is implementing solutions." Zara's voice came from deep within the aircraft's electrical compartment, muffled but determined. "Found something interesting. Hand me the fiber optic scope from my kit." Reeves reluctantly retrieved the requested tool, which looked like a miniature snake with a tiny camera on one end. It was clearly handmade, probably by the same grandfather who had built the electromagnetic detector. "What are you looking for?" Reeves asked. "Wire routing anomaly," Zara replied, her voice growing more distant as she worked deeper into the aircraft's interior. "There's supposed to be a 6-inch clearance between the primary grounding harness and the structural support beam, but the electromagnetic readings suggest they're in contact." "The computers would detect that," Reeves insisted. "Would they? If the contact is intermittent and only occurs under specific conditions, vibration, temperature expansion, electrical load variations, the computers might see it as separate minor issues rather than one underlying cause." For the next 2 hours, both teams worked with focused intensity. Bradley's group had implemented software updates and replaced 2 electrical control modules, their progress tracked on multiple screens that showed system status in real time. Their approach was methodical, efficient, and based on the most advanced diagnostic technology available. Zara, meanwhile, had traced wire pathways through increasingly cramped spaces, using tools that looked primitive by comparison but seemed to reveal information that the sophisticated computers missed. Her notebook filled with hand-drawn diagrams and measurements taken with calipers and rulers that had probably been used on aircraft before jet engines were invented. "This is ridiculous," Bradley announced loudly enough for everyone to hear. "We've already solved the problem using proven methods. Why are we waiting for someone to reinvent the wheel with museum pieces?" Commander Rostova, who had been observing both teams, stepped forward. "Because, Castellano, in my experience, problems that stump advanced diagnostic systems usually have causes that require different approaches to detect." "But Commander," Rebecca interjected, "our system diagnostics are showing significant improvements. The software updates have eliminated most of the error codes, and the new control modules are testing within normal parameters." "Most of the error codes," Commander Rostova noted. "What about the remaining issues?" Bradley consulted his screens, his confidence wavering slightly. "Minor anomalies. Probably just system integration delays. The computers need time to fully synchronize with the new components." From inside the aircraft, Zara's voice called out with sudden urgency. "Carmen, I need you to run the startup sequence while I monitor this connection. Reeves looked to Chief Vega, who nodded approval. As the aircraft's systems came online, Zara's electromagnetic detector began registering fluctuations that correlated precisely with the startup cycle. "There," Zara said, emerging from the electrical bay with grease-stained coveralls and a triumphant expression. "The primary grounding wire has worn through its insulation at exactly one point where it touches the support beam. When the aircraft systems are under electrical load, thermal expansion brings the bare wire into contact with the beam, creating an unintended antenna that broadcasts electromagnetic interference throughout the aircraft." She held up a small section of wire that showed clear wear marks. "It's intermittent because the contact depends on temperature, vibration, and electrical load. The computers see the resulting interference as separate minor issues affecting different systems rather than one source affecting multiple systems." Chief Vega examined the damaged wire through a magnifying glass. "How did the diagnostic computers miss this?" "Because they're designed to detect system failures, not system interactions," Zara explained. "The grounding fault isn't enough to trigger failure warnings in any individual system, but it creates interference patterns that affect overall performance in ways the computers interpret as minor, unrelated anomalies." Commander Rostova studied Zara's findings with the careful attention of someone who had learned not to dismiss unexpected solutions. "And your recommendation? Replace the damaged section of grounding wire and add additional insulation at the contact point. Total cost, about $15 in materials and 2 hours of labor." The contrast with Bradley's approach was stark. His team had spent thousands of dollars on new components and software updates to address symptoms while missing the underlying cause entirely. "Run a full systems check," Commander Rostova ordered. Over the next hour, Fighter 47 underwent comprehensive testing with both teams, monitoring the results. Bradley's team watched their sophisticated diagnostic displays with growing concern as some of the anomalies they thought they had fixed began reappearing. Meanwhile, Zara's simple wire repair had eliminated the electromagnetic interference that had been causing cascading problems throughout the aircraft's systems. "I don't understand," Bradley said, staring at his screens in disbelief. "The diagnostic computers indicated that software updates and component replacement would solve these issues." "The computers told you what was wrong with individual systems," Zara explained patiently, "but they couldn't see the pattern because they're not designed to look for simple causes of complex problems. Sometimes the most sophisticated diagnostic tool is still just a human being who knows how to observe and think systematically." Chief Vega looked between the two approaches, the high-tech diagnostic station that had cost more than most people's houses, and the collection of worn tools that looked like they belonged in a museum. "Outstanding work, Thorne. Your methodology identified the root cause, while more advanced approaches addressed only symptoms." That evening, the atmosphere in the barracks had shifted noticeably. While some recruits still clustered around Bradley to discuss the day's unexpected outcome, others approached Zara with new respect and curiosity about her unconventional methods. "How did you know to look for that specific problem?" asked Rebecca Manning, her earlier skepticism replaced by genuine interest. Zara was cleaning her tools with the same methodical care she'd shown during the diagnosis. "Experience with simpler aircraft taught me that electrical problems often have mechanical causes. The more complex a system becomes, the more ways small mechanical issues can create complicated electrical symptoms. But the diagnostic computers are designed specifically to detect these kinds of problems," Bradley insisted, though his earlier confidence had been replaced by defensive uncertainty. "They're designed to detect known problems," Zara corrected. "What happens when the problem is something the computers weren't programmed to recognize? when the cause and symptoms don't match the patterns in their databases. Carmen Reeves, who had worked alongside Zara during the investigation, nodded thoughtfully. I've been doing this for 6 years, and I've never seen anyone trace an electrical problem through pure observation like that. How do you develop that kind of intuition? By working on aircraft where you don't have sophisticated diagnostic computers to rely on, Zara replied. When you're maintaining a 40-year-old crop duster in rural Alaska, you learn to use your eyes, ears, and hands to understand what the machine is telling you. Those skills don't become obsolete just because the machines get more sophisticated. The conversation continued late into the evening, with Zara sharing stories of maintaining aircraft in conditions that would have challenged even experienced mechanics. Her experiences ranged from fixing helicopters in Arctic conditions with improvised tools to keeping vintage warbirds flying with parts that were no longer manufactured. The thing people don't understand about old aircraft, Zara explained, is that they force you to really understand how mechanical systems work. You can't just replace modules and run diagnostic scans. You have to trace problems through mechanical connections, understand how forces interact, and think about how wear and environmental factors affect performance over time. Bradley listened with growing frustration, clearly struggling to reconcile his faith in modern technology with the day's unexpected outcome. But surely you can't argue that old methods are better than new ones. These diagnostic systems represent decades of advancement in aviation technology. Nah, I'm not arguing that old is better than new, Zara replied calmly. I'm suggesting that different approaches reveal different types of information. Modern diagnostic systems are incredibly powerful for detecting known problems and monitoring system performance, but they have limitations, especially when dealing with interactions between systems or problems that don't fit expected patterns. So what are you saying? Rebecca asked. That we should abandon modern diagnostic tools and go back to working with hand tools and intuition? Zara shook her head. I'm saying that the best approach combines both. Use the sophisticated diagnostic systems to gather data and monitor known parameters, but don't let them replace your ability to observe, think, and investigate. Sometimes the most advanced computer in the world can't substitute for a human being who knows how to look at a problem from a different angle. The discussion was interrupted by the arrival of Chief Vega, who had been observing the conversation from the doorway. Interesting philosophical debate, he said, stepping into the room. But tomorrow you'll get a chance to put these ideas into practice. We're beginning advanced diagnostics training, and each team will be working on aircraft with real maintenance challenges. He paused, studying the group. Commander Rostova has decided to modify the training program based on today's results. Half your time will be spent learning to use the most advanced diagnostic systems available. The other half will focus on traditional investigative techniques and fundamental mechanical understanding. Sir, Bradley asked, does this mean our modern approach was wrong? Vega considered the question carefully. It means that relying exclusively on any single approach, whether it's cutting-edge technology or traditional methods, creates blind spots. The best mechanics combine multiple approaches to understand aircraft systems completely. As the group dispersed, Zara found herself alone with her tools, thinking about the unexpected turn her career had taken. She had come to Blackwater expecting to struggle with technology far beyond her experience. Instead, she had discovered that her supposedly obsolete skills filled gaps that even the most advanced systems couldn't address. Outside the barracks, the sound of jet engines warming up for night training flights created a constant background hum. Each of those aircraft represented millions of dollars in technology and engineering, but they still depended on the fundamental mechanical principles that Zara had learned working on machines that were older than some of her fellow recruits. Tomorrow would bring new challenges and the opportunity to prove that sometimes the most sophisticated solution wasn't the most effective one. But tonight, Zara cleaned her grandfather's tools with the same care he had taught her, preparing for whatever problems the most advanced aircraft in the world might present. The rain had returned to Blackwater Naval Air Station, drumming against the hangar roofs with the persistence that defined Pacific Northwest weather. But inside Hangar 7, the atmosphere was electric with anticipation as the recruits prepared for their most challenging assignment yet. Commander Rostova stood before a massive display screen showing technical specifications for the Navy's newest acquisition, an experimental F-35C variant designated Lightning II-X, equipped with next-generation systems that push the boundaries of current aviation technology. The aircraft represented not just $50 million in hardware, but years of research and development that would influence fighter design for decades to come. "Ladies and gentlemen," Commander Rostova announced, "what you see here is the most advanced fighter aircraft ever built. It incorporates experimental stealth technologies, adaptive flight control systems, and integrated electronic warfare capabilities that exist nowhere else in the world." The image on screen showed an aircraft that seemed to absorb light itself, its surfaces flowing in curves that suggested both incredible speed and otherworldly beauty. Even to Zara's experienced eye, it looked more like a piece of alien technology than anything built by human hands. This aircraft arrived yesterday for its final evaluation phase before full production approval, Commander Rostova continued. Unfortunately, it has developed a series of mysterious malfunctions that have stumped the manufacturer's most experienced technicians. Ground testing reveals intermittent system failures that prevent the aircraft from achieving full operational capability. Bradley raised his hand immediately. "Commander, what kind of diagnostic data is available? Have the manufacturer's teams shared their findings?" "Extensive diagnostic data," Commander Rostova replied. "The aircraft's onboard computers have logged thousands of error messages, system warnings, and performance anomalies. 3 separate technical teams have spent the past month trying to identify patterns or root causes." She gestured to a stack of printouts that stood nearly 3 feet high. That represents the diagnostic output from the aircraft's systems over the past 30 days. Despite access to the most advanced troubleshooting equipment available, including direct consultation with the aircraft's designers, no one has been able to identify why this fighter cannot achieve stable operation. Zara studied the aircraft image with growing interest, while her fellow recruits focused on the impressive technical specifications scrolling past on the display. She found herself thinking about the fundamental challenges of integrating so many complex systems into a single platform. "Your assignment," Commander Rostova announced, "is to work in teams to identify and solve whatever is preventing this aircraft from achieving full operational status. You'll have access to all the diagnostic data collected so far, plus the manufacturer's technical teams for consultation." She paused, scanning the group. "However, I want to be clear about the stakes involved. This aircraft represents the future of naval aviation. If we cannot solve these problems, the entire program may be cancelled, affecting thousands of jobs and compromising our military capabilities for years to come." The teams were divided differently this time, with Commander Rostova personally selecting the partnerships. Bradley found himself paired with Carmen Reeves, while Zara was assigned to work with Rebecca Manning. The change created interesting dynamics, as each team now combined high-tech and traditional approaches rather than keeping them separate. "I have to admit," Rebecca said as they approached the Lightning II exit for the first time, "yesterday's results made me think about whether I've been too focused on computer diagnostics. The experimental fighter was housed in a separate section of Hangar 7, surrounded by security barriers and monitoring equipment that tracked every person who approached. Up close, the aircraft's otherworldly appearance was even more pronounced. Its surfaces seemed to shift and flow in ways that challenged the eye's ability to focus. "It's beautiful," Zara murmured, walking slowly around the fighter's perimeter, "but it's also incredibly complex. Look at all these system integration points." She was referring to the numerous access panels and connection ports that allowed maintenance crews to interface with the aircraft's various systems. Unlike conventional fighters, which had clear separation between mechanical and electronic components, the Lightning II-X appeared to integrate everything into unified systems that blurred traditional boundaries. Rebecca connected her laptop to the aircraft's primary diagnostic port and began downloading the accumulated error logs. "Dentil. Wow," she said, watching data stream across her screen. "This is incredible. The aircraft monitors literally thousands of parameters continuously." Meanwhile, Zara had begun her own investigation using her traditional tools. Her electromagnetic detector immediately registered unusual activity, not the clear interference pattern she had found in Fighter 47, but something more subtle and complex. "Rebecca," she said, studying her readings, "take a look at these electromagnetic signatures. Do they correlate with any of the error patterns in your diagnostic data?" Rebecca pulled up several graphs showing system failures over time. "There do seem to be correlations," she said slowly. "When electromagnetic activity spikes, certain types of errors increase, but the patterns are incredibly complex, not like the simple interference we found yesterday." Over the next several hours, both teams worked with intense focus on the challenging puzzle presented by the Lightning II-X. Bradley and Carmen had deployed an impressive array of diagnostic equipment, creating a mobile command center that could monitor dozens of aircraft systems simultaneously. "The problem," Bradley announced during a mid-morning briefing, "appears to be systemic instability caused by conflicts between the aircraft's various computer systems. The integration between flight control, stealth management, and electronic warfare systems is creating computational bottlenecks that cause cascading failures." His analysis was supported by extensive data showing how system loads increased, until certain thresholds triggered automatic shutdowns designed to prevent damage. It was sophisticated work that demonstrated deep understanding of complex computer architectures. "Our recommendation," Carmen added, "is systematic software optimization to reduce computational conflicts. We've identified 17 specific areas where improved code efficiency could eliminate the bottlenecks causing system failures." Commander Rostova studied their findings carefully. "How long would this optimization process take?" "Probably 6 months," Bradley replied. "The software modifications would need extensive testing to ensure they don't create new problems or compromise safety systems." "And the cost?" Carmen consulted her notes. "Estimated at $2 million for software development, plus additional costs for testing and validation." Commander Rostova turned to Zara and Rebecca. "What are your findings?" Rebecca presented their data, which painted a different picture entirely. "We've identified electromagnetic interference patterns that suggest the aircraft's advanced systems are creating internal conflicts that manifest as computational problems." "But it's not simple interference like yesterday," Zara added. "The Lightning II-X uses experimental materials and geometries that create electromagnetic effects nobody fully understands yet. The aircraft's own stealth technology may be interfering with its electronic systems in unexpected ways." She opened her notebook to a page covered with hand-drawn diagrams and calculations. The stealth surfaces are designed to absorb and deflect electromagnetic radiation from external sources, radar, communications, electronic weapons. But they're also affecting electromagnetic radiation generated by the aircraft's own systems. "Explain," Commander Rostova said. "Think of it like an echo chamber," Zara continued. "The stealth materials that make the aircraft invisible to enemy radar are also trapping and redirecting electromagnetic energy from the aircraft's own computers and sensors. This creates interference patterns that change constantly as the aircraft's systems operate." Rebecca nodded, pointing to her laptop screen. "The computational problems Bradley identified aren't caused by software inefficiency. They're caused by the aircraft's computers fighting electromagnetic interference that's being generated and amplified by the aircraft's own stealth technology." That's impossible," Bradley interrupted. "The aircraft was designed by teams of experts who would have anticipated and prevented that kind of problem." "Would they?" Zara asked. "This aircraft incorporates technologies that have never been combined before. The stealth materials are experimental, the electronic systems are cutting edge, and the integration between them is unprecedented. Nobody could predict every possible interaction." Commander Rostova studied both analyses carefully. "Thorne, you're suggesting that the aircraft's most advanced feature, its stealth capability, is also causing its operational problems?" "Yes, ma'am. And more specifically, I think I know where the problem is located and how to fix it." The hangar fell silent. Even Bradley stopped shuffling through his diagnostic data to listen. The electromagnetic interference patterns suggest that the primary problem is in the aft electronics bay, where the stealth control systems interface with the main flight computers, Zara explained. The stealth materials in that area are creating a resonance effect that amplifies electromagnetic noise from the computer systems. She traced a finger along one of her diagrams. "It's like having a guitar string that vibrates in harmony with other strings. The electromagnetic energy from the computers resonates with the stealth materials, creating interference that affects systems throughout the aircraft." "And your solution?" Commander Rostova asked. "Electromagnetic shielding in the electronics bay, specifically designed to prevent resonance between the stealth materials and computer systems. It would require modifying the internal structure, but the cost would be minimal compared to months of software development." Rebecca looked up from her laptop with growing excitement. "The data supports this theory. When I overlay the electromagnetic readings with the system failure logs, there's a direct correlation. Every major system crash corresponds with electromagnetic spikes from the aft electronics bay." Bradley studied the proposed solution with obvious skepticism. "Commander, this is pure speculation. We have concrete evidence of software conflicts and computational bottlenecks. You can't solve computer problems with electromagnetic shielding." "Can't you?" Commander Rostova asked. "Yesterday, we discovered that electrical problems can have mechanical causes. Today, we're considering whether computational problems might have electromagnetic causes." She walked closer to the Lightning 2X, studying its alien-like surfaces. "The fundamental question is whether we trust diagnostic computers to identify problems in systems they were never designed to analyze, or whether we investigate the possibility that unprecedented technology creates unprecedented problems." Chief Vega stepped forward. "Commander, with respect, we're talking about recommending modifications to a $50 million experimental aircraft based on readings from equipment that looks like it belongs in a museum." Zara felt the familiar weight of skepticism. But this time something was different. Rebecca was nodding in agreement with her analysis, and even Carmen Reeves was studying the electromagnetic data with obvious interest. "Chief Vega," Zara said respectfully, "may I demonstrate something?" She pulled out a small device that looked like a modified radio, another piece of her grandfather's handmade equipment. This is an electromagnetic resonance detector. It can identify when electromagnetic fields are creating harmonic interference. Moving the device systematically around the Lightning U2X, she traced patterns that seemed random until she reached the aft electronics bay. Suddenly, the device began emitting a distinct tone that fluctuated in harmony with the aircraft's system cycles. "There," she said, pointing to a specific panel. "The electromagnetic resonance is strongest right here, where the stealth control computers interface with the main flight systems." Rebecca confirmed the finding on her laptop. That location corresponds exactly with the highest concentration of system errors in the diagnostic logs. Bradley approached with his own electromagnetic measurement equipment, a sophisticated device that displayed readings on a digital screen. "I'm not detecting anything unusual," he announced after scanning the same area. "What frequency range is your equipment calibrated for?" Zara asked. Bradley consulted his device specifications. "Standard electromagnetic frequencies used in aviation electronics, 20 Hz to 10 GHz. "The resonance I'm detecting is at 14 GHz, Zara replied. "Just outside your equipment's range. It's a harmonic frequency created by the interaction between the stealth materials and the computer systems." She explained that her grandfather's equipment had been modified over decades to detect electromagnetic anomalies that conventional instruments missed. While it looked primitive, it had been calibrated through years of practical experience to identify interference patterns that didn't appear in standard frequency ranges. Commander Rostova made a decision that surprised everyone. "I want both approaches tested. Bradley's team will begin software analysis to identify and resolve computational conflicts. Zara's team will investigate electromagnetic shielding solutions for the aft electronics bay." "Commander," Bradley protested, "we're talking about modifying an experimental aircraft based on unproven theories. The manufacturer's teams have already ruled out electromagnetic interference as a cause." "Have they?" Commander Rostova asked. "Or have they ruled out electromagnetic interference within the frequency ranges their equipment can detect?" She turned to address both teams. "What we're dealing with here is the integration of technologies that have never been combined before. The manufacturers designed each system individually and then integrated them based on theoretical models. But theory and reality don't always match, especially when dealing with experimental materials and unprecedented system integration. The next phase of testing would prove revelatory in ways none of them anticipated." Bradley's team dove deep into the aircraft's software architecture, deploying diagnostic tools that could analyze millions of lines of code and identify potential conflicts between different systems. Their approach was methodical and comprehensive, based on proven techniques for troubleshooting complex computer systems. Meanwhile, Zara and Rebecca focused on understanding the physical interactions between the aircraft's various components. Using a combination of traditional investigative techniques and modern measurement tools, they traced electromagnetic pathways through the Lightning IIX's structure. "This is fascinating," Rebecca said, watching Zara work with equipment that seemed to reveal information invisible to conventional instruments. "I never realized how much electromagnetic activity modern aircraft generate internally." "Most people don't," Zara replied, carefully mapping electromagnetic field patterns with her grandfather's modified instruments. "We think of electromagnetic interference as something that comes from outside, enemy jamming, radio broadcasts, power lines. But complex electronic systems create their own electromagnetic environments that can interfere with their own operation. The investigation led them through access corridors and maintenance spaces that few people ever saw. The Lightning II case's internal structure was a marvel of engineering efficiency, with systems packed into every available space. But as they traced electromagnetic pathways, a disturbing pattern emerged. "Rebecca, look at this," Zara said, pointing to her hand-drawn diagrams. "The stealth materials aren't just affecting electromagnetic radiation in the aft electronics bay. They're creating a resonance network throughout the entire aircraft." Rebecca studied the patterns with growing understanding. It's like the aircraft's structure has become a giant antenna that's tuned to frequencies generated by its own systems. Exactly. And because the stealth materials were designed to manipulate electromagnetic radiation in specific ways, they're amplifying certain frequencies while suppressing others. The result is electromagnetic chaos that affects every system on the aircraft. Meanwhile, Bradley's team had made significant progress in their software analysis. They had identified numerous inefficiencies in the code that integrated different systems, and their proposed optimizations showed promising results in computer simulations. "We found the problem," Bradley announced during an afternoon briefing. "The integration software wasn't designed to handle the computational load created by simultaneous operation of all the aircraft systems. When flight control, stealth, management, and electronic warfare systems operate together, they create processing bottlenecks that cause system crashes." Carmen presented their findings with impressive detail. "Our proposed software modifications will reduce computational overhead by 37% and eliminate the bottlenecks that cause cascading failures. We can implement these changes using existing hardware without any physical modifications to the aircraft." Commander Rostova studied their analysis carefully. "How confident are you that software optimization will solve all the reported problems?" "Very confident," Bradley replied. "Our simulations show that the software modifications eliminate the computational conflicts that cause system instabilities." "And what about the electromagnetic anomalies that Thorne's team detected?" Bradley exchanged glances with Carmen before responding. "Commander, we believe those readings are artifacts of the system failures rather than their cause. When computer systems crash and restart repeatedly, they can generate electromagnetic noise that appears to be interference, but is actually just a symptom of the underlying software problems." It was a reasonable explanation that fit with conventional understanding of aircraft systems. But Zara had spent too many years troubleshooting complex problems to accept surface explanations without deeper investigation. "Bradley," she said respectfully, "would you be willing to test that theory? If the electromagnetic anomalies are symptoms of software problems, they should disappear when your software optimizations are implemented." "Of course," Bradley agreed confidently. "When the software modifications eliminate the computational conflicts, any electromagnetic artifacts should disappear automatically." Commander Rostova approved a controlled test of both approaches. Bradley's team would implement their software optimizations while Zara's team monitored electromagnetic activity throughout the process. If the software fixes eliminated the electromagnetic anomalies, it would confirm that the computer problems were the root cause. If electromagnetic interference persisted, it would suggest that Zara's theory about resonance effects might be correct. The test began the following morning, with Bradley's team loading their optimized software into the Lightning IIX's computer systems. The process required several hours as modified code was carefully integrated with existing systems and tested for compatibility. Zara positioned her electromagnetic monitoring equipment at key points throughout the aircraft, creating a network of sensors that could track interference patterns in real time. Rebecca assisted by correlating the electromagnetic readings with diagnostic data from the aircraft's onboard computers. Software integration complete, Bradley announced. All systems show normal startup parameters and optimized processing efficiency. Initial tests were encouraging. The aircraft's systems came online smoothly, and diagnostic computers reported significantly fewer error messages than previous startups. Bradley's software optimizations had clearly improved system performance and eliminated many of the computational conflicts that had been causing problems. "Outstanding work," Chief Vega commented, watching system status displays that showed stable operation across all major aircraft functions. "It appears the software approach has resolved the primary issues." But Zara's electromagnetic monitors told a different story. While the computer systems were operating more efficiently, the fundamental electromagnetic resonance patterns remained unchanged. The aircraft's stealth materials continued to interact with electromagnetic radiation from the computer systems, creating interference that the improved software was simply handling more effectively. "The electromagnetic problems are still there," Zara reported. "The software optimizations have made the computer systems more resilient to interference, but they haven't eliminated the source of the interference." Rebecca confirmed the findings on her diagnostic displays. "The error logs show fewer failures, but when I analyze the data more carefully, I can see that the systems are still fighting electromagnetic interference. They're just handling it better now." Bradley studied their readings with obvious frustration. "But the aircraft is operating normally. System performance is within acceptable parameters. What difference does it make if there's some residual electromagnetic activity?" "It makes a difference," Commander Rostova said quietly, "because we're not just testing whether this aircraft can function, we're testing whether it can function reliably under combat conditions, where system failures can mean the difference between life and death." She turned to address both teams. "Your software optimizations have clearly improved the aircraft's performance, Bradley. But if underlying electromagnetic problems persist, they could cause failures under stress conditions that we can't predict or simulate." Zara nodded. "The electromagnetic resonance effects we're detecting will get worse under certain conditions: high power output, extreme maneuvers, electronic warfare environments. The improved software might handle normal interference, but it could still fail when the interference increases beyond current levels." The implications were sobering. The Lightning X might perform acceptably during controlled testing, but fail catastrophically during actual combat missions. The difference between a $50 million fighter that worked in ideal conditions and one that worked under combat stress was the difference between success and disaster. Commander Rostova made another crucial decision. Continue with both approaches. Bradley, implement your software optimizations throughout the aircraft's systems. Zara, develop electromagnetic shielding solutions for the most critical interference sources. "Commander," Bradley protested, "we've already solved the problem. Additional modifications just add complexity and potential failure points." "Have we solved the problem?" Commander Rostova asked. "Or have we masked it? There's a difference between making systems more resilient to interference and eliminating the interference itself." Over the following days, both teams worked with renewed intensity on their respective approaches. Bradley's software optimizations continued to show impressive results, with the Lightning II-X achieving stable operation across a wide range of test conditions. System crashes had been virtually eliminated, and performance metrics exceeded the manufacturer's specifications. Meanwhile, Zara had begun developing electromagnetic shielding solutions that addressed the resonance effects she had identified. Working with materials engineers from the base's research division, she designed modifications that would prevent electromagnetic interference without compromising the aircraft's stealth capabilities. The challenge, she explained to Rebecca, is that we need to stop electromagnetic resonance without affecting the stealth material's ability to absorb external radar signals. It's like trying to create a one-way mirror for electromagnetic radiation. The solution she developed was elegant in its simplicity. By adding carefully designed electromagnetic barriers at specific points in the aircraft's structure, she could interrupt the resonance networks without affecting the stealth surface's interaction with external electromagnetic sources. "It's brilliant," Rebecca said, studying Zara's designs. "You're not changing how the stealth materials work. You're just preventing them from interfering with the aircraft's own systems." The shielding modifications were relatively simple to implement, requiring the installation of specially designed materials in key locations throughout the aircraft's structure. Unlike Bradley's software approach, which required extensive testing and validation, the electromagnetic shielding could be installed and tested quickly. When both modifications were implemented together, the results exceeded everyone's expectations. The Lightning II DQ2s achieved not just stable operation, but performance levels that surpassed the manufacturer's most optimistic projections. System efficiency increased dramatically, while electromagnetic interference dropped to virtually undetectable levels. "Remarkable," Chief Vega commented, watching test results that showed the aircraft operating flawlessly under conditions that had previously caused system failures. Both approaches together have created synergistic effects that neither could achieve alone. Bradley studied the combined results with obvious amazement. "I don't understand how electromagnetic shielding could improve software performance by this much. The effects are far greater than simple elimination of interference should produce." Zara smiled, remembering similar surprises from her years working on simpler aircraft. When you eliminate interference that systems have been fighting constantly, they can operate at efficiency levels they were designed for but never achieved. It's like removing a weight that someone has been carrying so long they forgot it was there. The test results vindicated both approaches while demonstrating that complex problems often required multiple solutions. The software optimizations had made the aircraft's systems more efficient and resilient, while the electromagnetic shielding had eliminated the interference that prevented those systems from reaching their full potential. Commander Rostova reviewed the comprehensive test data with obvious satisfaction. "Outstanding work, all of you. You've not only solved the immediate problems, but developed solutions that will influence aircraft design for years to come." She paused, studying the comparative results. "More importantly, you've demonstrated that the most effective approach to complex problems combines multiple perspectives rather than relying exclusively on any single methodology." That evening, the atmosphere in the barracks reflected the day's success, but also a new understanding of how different approaches to problem-solving could complement rather than compete with each other. Bradley approached Zara with obvious respect, carrying printouts of the combined test results. "I owe you an apology," he said quietly. "I was so convinced that modern diagnostic methods were superior that I dismissed the possibility that traditional approaches might reveal information that computers miss." Zara looked up from cleaning her tools with the same methodical care she always showed. "You don't owe me an apology, Bradley. Your software optimizations were essential to solving the problem. The aircraft couldn't have achieved these performance levels without both approaches working together." "But you were right about the electromagnetic interference," Rebecca added, joining the conversation. "The diagnostic computers couldn't detect problems that were outside their program parameters." "And you were right about software optimization," Zara replied to Bradley. "The aircraft systems needed to be more efficient before electromagnetic shielding could achieve its full effect. Neither approach would have been completely successful alone." Carmen Reeves, who had worked with both teams during the testing, nodded thoughtfully. It's like the aircraft needed both mechanical and digital solutions to reach its full potential. The hardware and software problems were interconnected in ways that required interconnected solutions. The conversation continued as other recruits joined, creating an impromptu discussion about the relationship between traditional mechanical skills and modern technological approaches. What emerged was a new understanding that the best solutions often combined multiple methodologies rather than favoring one over another. "The thing that strikes me," Bradley said, studying Zara's worn tools with new appreciation, "is that your grandfather's equipment detected problems that million-dollar diagnostic systems missed. How is that possible?" Zara considered the question carefully. "I think it's because my grandfather's tools were designed by someone who understood that problems don't always fit into expected categories. Modern diagnostic systems are incredibly sophisticated, but they're designed to find known types of problems within predetermined parameters." She picked up the electromagnetic detector that had identified the resonance effects in the Lightning II-X. This device was modified over decades by someone who encountered problems that didn't fit conventional patterns. Each modification was based on practical experience with real-world situations that textbooks don't cover. "So experience trumps technology?" Rebecca asked. "No," Zara replied. "Experience and technology complement each other. The best diagnostic approach uses technological tools to gather data and traditional investigative skills to interpret that data in ways computers can't." Chief Vega, who had been listening from the doorway, stepped into the conversation. "What you've all discovered," he said, "is that complex systems require multiple approaches to understand completely. The Lightning II-X couldn't be fixed by software optimization alone or electromagnetic shielding alone. It required both, plus the insight to recognize how they work together." He gestured toward the technical manuals and diagnostic printouts scattered around the room. "Modern aircraft represent the integration of thousands of technologies, many of which interact in ways their designers never anticipated. Understanding these interactions requires both technological sophistication and fundamental mechanical intuition." "Daryl!" The discussion was interrupted by an announcement over the base communication system. "All personnel involved in Lightning II-X testing report to Hangar 7 immediately for emergency briefing." The group exchanged concerned glances as they quickly gathered their equipment and headed toward the hangar. Emergency briefings at Blackwater Naval Air Station were rare and usually indicated serious problems that required immediate attention. When they arrived at Hangar 7, they found Commander Rostova waiting with several people they didn't recognize, civilians in expensive suits who had the bearing of high-ranking officials or corporate executives. The Lightning II-X sat nearby, surrounded by additional security personnel and monitoring equipment. "Ladies and gentlemen," Commander Rostova announced, "I want you to meet Dr. Patricia Hawthorne, Chief Engineer for the Lightning II-X program, and Marcus Chen, Program Director." For the manufacturer, Dr. Hawthorne stepped forward, her expression serious but intrigued. "We've been monitoring your testing results remotely, and frankly, we're amazed by what you've accomplished. The performance improvements you've achieved exceed anything we thought possible with this aircraft." Marcus Chen nodded in agreement. "The combined software and hardware modifications you've developed have solved problems that our teams have been working on for months. We need to understand how you identified solutions that our most experienced engineers missed." Commander Rostova gestured toward the assembled recruits. "Dr. Hawthorne, Mr. Chen, meet the team that revolutionized your aircraft. They combined traditional investigative techniques with modern diagnostic technology to identify and solve problems that conventional approaches couldn't address." Bradley stepped forward nervously. Sir, ma'am, we just applied standard troubleshooting procedures and worked together to understand the aircraft's systems. Standard procedures, Dr. Hawthorne repeated with obvious skepticism. Mr. Castellano, your software optimizations required insights into system integration that our programming teams didn't achieve after months of analysis. How did you identify computational bottlenecks that our diagnostic systems missed? Actually, Bradley replied with surprising honesty, the breakthrough came from combining my software analysis with electromagnetic interference detection using equipment that I initially thought was obsolete. He gestured towards Zara. Specialist Thorne identified electromagnetic problems that our computers couldn't detect because they occurred outside the frequency ranges our diagnostic systems monitor. Dr. Hawthorne turned her attention to Zara with obvious interest. Specialist Thorne, our teams conducted extensive electromagnetic compatibility testing during the aircraft's development. How did you detect interference that escaped our analysis? Zara felt the familiar nervousness of being scrutinized by experts, but her voice remained steady. Ma'am, your testing probably focused on ensuring that the aircraft systems could resist external electromagnetic interference, enemy jamming, radar, communication signals. But the problems we found were caused by electromagnetic interactions between the aircraft's own systems. Explain, Marcus Chen requested. The Lightning 2X integrates technologies that have never been combined before, Zara continued. The stealth materials, the computer systems, the electronic warfare equipment, each was designed and tested individually. But when they're all operating together, they create electromagnetic effects that nobody anticipated. She opened her notebook to diagrams showing the electromagnetic pathways they had traced through the aircraft. The stealth materials that make the aircraft invisible to enemy radar also affect electromagnetic radiation generated by the aircraft's own systems. This creates resonance effects that interfere with system operation in ways that don't show up in conventional testing. Dr. Hawthorne studied the hand-drawn diagrams with growing amazement. These patterns, how did you map electromagnetic fields with this level of detail? Our most sophisticated equipment couldn't generate this kind of analysis. Modified equipment built by my grandfather, Zara explained. It's designed to detect electromagnetic anomalies that don't appear in standard frequency ranges or conventional interference patterns. Marcus Chen examined Zara's tools with the curiosity of someone encountering technology he'd never seen before. This equipment looks like it was built decades ago. How can it outperform modern diagnostic systems? Because it was designed by someone who understood that problems don't always fit into expected categories, Zara replied. Modern diagnostic systems are programmed to find specific types of problems. This equipment was built to find problems that don't fit known patterns. Dr. Hawthorne exchanged glances with Marcus Chen before turning back to the group. We need to understand something. The Lightning 2X program represents $3 billion in development costs and contracts for hundreds of aircraft. If your modifications can reliably solve the problems we've been struggling with, they could save the entire program. But Marcus Chen added, we also need to understand whether these solutions will work consistently across different aircraft and operating conditions. We can't recommend production changes based on results from a single test aircraft. Commander? Rostova stepped forward. Dr. Hawthorne, Mr. Chen, what exactly are you proposing? We want to bring this team to our primary development facility to work directly with our engineering staff, Dr. Hawthorne replied. If they can replicate these results with our full Lightning 2X test fleet, we'll implement their modifications across the entire production program. The offer was stunning in its implications. Instead of completing their training at Blackwater Naval Air Station, they would be working directly with the aircraft manufacturer on problems that affected national defense capabilities and billions of dollars in military contracts. "There's just one condition," Marcus Chen added. "We need the entire team. The software optimizations and electromagnetic solutions work together in ways that require both approaches. We can't achieve these results using just one methodology or the other." Bradley looked at Zara with new respect. "You mean we'd be working together on the manufacturer's development team?" "Exactly," Dr. Hawthorne confirmed. "Your combined approach has solved problems that neither software optimization nor hardware modification could address individually. We need both perspectives to ensure reliable solutions." Commander Rostova addressed the group. "This is an unprecedented opportunity, but it's also a significant responsibility. The Lightning 2X program affects not just military capabilities, but thousands of jobs and the future of naval aviation. Are you prepared for that level of responsibility?" Zara looked around at her fellow recruits, seeing the same mixture of excitement and apprehension in their faces that she felt herself. A few weeks ago, she had been dismissed as a maintenance failure, relegated to support duties because her methods were considered too slow and outdated for modern aircraft. Now she was being offered the opportunity to work on the most advanced fighter jet ever built, using the same supposedly obsolete tools and techniques that had been mocked and dismissed. The irony wasn't lost on her. But more importantly, she recognized the chance to prove that different approaches to problem solving could work together to achieve results that neither could accomplish alone. "Yes, ma'am," she replied, speaking for the entire group. "We're ready." As the briefing concluded and the implications of their new assignment began to sink in, Zara found herself looking at the Lightning 2X with new understanding. The aircraft had taught her that the most sophisticated technologies still depended on fundamental principles that her grandfather would have recognized. Tomorrow would bring new challenges and the opportunity to work with the most advanced aircraft development team in the world. But tonight, she cleaned her grandfather's tools with the same methodical care he had taught her, preparing for whatever problems the future of aviation might present. The journey from dismissed support staff to essential team member had been unexpected, but it reinforced a lesson she'd learned long ago. Sometimes the most important contributions come from perspectives that others overlook. In a world obsessed with the latest technology, there was still value in understanding how things really work at the most fundamental level. And sometimes, just sometimes, the oldest solutions were exactly what the newest problems needed. 6 months later, Zara stood in the manufacturer's primary development facility at Edwards Air Force Base, watching the final preparations for the most critical test in the Lightning 2X program's history. The Pentagon had arranged a live demonstration for defense officials from 12 allied nations, with procurement contracts worth $20 billion hanging in the balance. The facility buzzed with nervous energy as engineers, test pilots, and military officials prepared for what would either validate years of development work or expose fatal flaws that could end the program entirely. 3 Lightning 2X aircraft sat on the flight line, their surfaces gleaming like liquid metal under the California sun. "Thorne," called Dr. Patricia Hawthorne, approaching with a tablet displaying real-time system monitoring data. "Final systems check shows all aircraft operating within optimal parameters. Your electromagnetic modifications are performing flawlessly across the entire test fleet." Over the past months, Zara had worked closely with the manufacturer's engineering teams to implement her electromagnetic shielding solutions across multiple aircraft. The process had revealed additional complexities that required constant refinement of her original designs. but the results consistently exceeded expectations. Bradley emerged from the nearest aircraft, his uniform marked with the grease stains that had become badges of honor for their team. His software optimizations had evolved far beyond their original scope, incorporating machine learning algorithms that could adapt to electromagnetic interference patterns in real time. Aircraft 773 is ready, he announced. The adaptive software is showing 98% efficiency, and all systems are responding perfectly to the electromagnetic environment modifications. The collaboration between their different approaches had produced innovations that neither could have achieved independently. Bradley's software now incorporated feedback from Zara's electromagnetic monitoring systems, while her shielding designs were informed by his analysis of computational loads and system interactions. Rebecca Manning approached carrying a diagnostic tablet that displayed data streams from all 3 test aircraft. Her role had evolved into system integration coordination, ensuring that hardware and software modifications worked together seamlessly. Global Hawk surveillance drones are reporting clear weather and optimal visibility for the demonstration, she announced. Defense officials from all participating nations have confirmed attendance, and the test pilots are ready for final briefing. The demonstration would push the Lightning II-2X aircraft through their most demanding performance scenarios yet. Unlike controlled testing in laboratory conditions, today's flights would simulate actual combat missions with multiple aircraft operating together under electronic warfare conditions that would stress every system to its limits. General Patricia Morrison, who had returned from Washington specifically for the demonstration, gathered the team for a final briefing. Her presence indicated the level of attention this test had attracted from the highest levels of military leadership. "Ladies and gentlemen," General Morrison announced, "today's demonstration represents the culmination of the most ambitious fighter aircraft program in military history. Success here determines not just the future of the Lightning II-X, but America's ability to maintain air superiority for the next generation." She gestured toward the aircraft waiting on the flight line. These fighters incorporate technologies that didn't exist 5 years ago. More importantly, they incorporate solutions to problems that our most experienced engineers couldn't solve until your team developed new approaches to aircraft system integration. The weight of responsibility was immense. Failure during today's demonstration wouldn't just embarrass the development team. It could compromise national security relationships and cost thousands of jobs across the defense industry. Marcus Chen, the program director, stepped forward with updates from the international delegation. Representatives from allied nations have arrived with their technical advisors. They're particularly interested in the electromagnetic compatibility modifications, since several countries have experienced similar problems with their own advanced aircraft programs. "What kind of problems?" Zara asked. "System integration failures during multi-aircraft operations," Chen replied. "When multiple stealth fighters operate in close proximity, their electromagnetic signatures can interfere with each other in ways that cause cascading system failures. Your solutions may address problems that extend far beyond the Lightning II-X program." The implications were staggering. If electromagnetic interference between aircraft could cause system failures during coordinated missions, it could compromise the effectiveness of entire fighter squadrons. The solutions they had developed for individual aircraft might be essential for multi-aircraft operations that formed the backbone of modern air power. Colonel Sarah Chen, who had been instrumental in supporting their unconventional approach, at Blackwater Naval Air Station, arrived with final meteorological data. Weather conditions are optimal for all planned test scenarios. Wind speeds are minimal, visibility unlimited, and atmospheric electromagnetic activity is at baseline levels. She paused, studying the assembled team. "I want you to know that observers from military academies worldwide are watching today's results. The methodologies you've developed are already being incorporated into maintenance training programs, and today's demonstration will influence aircraft design philosophy for decades." As the morning progressed, international delegates arrived. In a steady stream of official vehicles, defense ministers, Air Force commanders, and technical advisors from allied nations gathered in the observation facility that overlooked the test range. The diversity of uniforms and languages underscored the global significance of the Lightning II-X program. Dr. Hawthorne approached Zara with a final systems report. "All electromagnetic monitoring stations are showing normal baseline readings. Your modifications have eliminated the resonance effects that were causing system instabilities, and the aircraft are performing at levels that exceed our most optimistic projections." "What about multi-aircraft interference?" Zara asked, remembering Marcus Chen's comments about problems experienced by other countries. "That's today's ultimate test," Dr. Hawthorne replied. "We'll be operating 3 aircraft in close formation, under electronic warfare conditions. If electromagnetic interference between aircraft causes system failures, it will happen during today's demonstration." The first phase of testing involved individual aircraft performance under increasingly demanding conditions. Each Lightning II-X took off separately and flew through scenarios that stressed every system, while international observers monitored performance data in real time. From the observation facility, Zara watched Aircraft 771 execute maneuvers that seemed to defy physics. The fighter's surfaces rippled and flexed in ways that conventional aircraft couldn't achieve, while its stealth systems rendered it nearly invisible to tracking radar. "Incredible," murmured Air Marshal Elizabeth Thompson from the Royal Air Force, studying performance data on her tablet. "These aircraft are achieving efficiency levels that our modeling suggested were theoretically impossible." Bradley monitored software performance from a mobile command center that could track computational loads across all aircraft systems simultaneously. "Processing efficiency is holding steady at optimal levels," he announced. "The adaptive algorithms are compensating automatically for electromagnetic variations without any manual intervention." The second phase involved 2 aircraft operating together in scenarios that simulated coordinated combat missions. This was where electromagnetic interference between aircraft had caused failures in previous programs, as multiple stealth fighters created overlapping electromagnetic fields that could overwhelm individual system safeguards. Zara watched her, monitoring equipment carefully as both aircraft came within close proximity during simulated air-to-air combat maneuvers. The electromagnetic readings showed complex interactions between the aircraft, but the shielding modifications were preventing interference from reaching critical levels. "No system warnings," Rebecca reported from her integration monitoring station. "Both aircraft are maintaining full operational capability despite electromagnetic field overlap." General Morrison observed the proceedings with obvious satisfaction. "Outstanding performance. These aircraft are demonstrating capabilities that our intelligence services reported were impossible to achieve reliably." The final phase would be the ultimate test. 3 aircraft operating in close formation while subjected to electronic warfare conditions that simulated the most challenging combat environments. Electronic warfare specialists activated jamming, systems that filled the airspace with electromagnetic interference, designed to disrupt aircraft communications, navigation, and targeting systems. "Electronic warfare simulation active," announced the test director. "All aircraft are now operating under maximum electromagnetic stress conditions." Zara's monitoring equipment registered massive increases in electromagnetic activity as the jamming systems created interference levels that would have overwhelmed unmodified aircraft. But the Lightning II-X fighters continued operating normally, their systems protected by the shielding modifications she had developed. "This is remarkable," commented Defense Minister Klaus Richter from Germany, watching aircraft performance data that showed stable operation despite electromagnetic interference that should have caused system failures. These fighters are maintaining full capability under conditions that would disable conventional aircraft. Bradley's software optimizations were proving equally crucial. The adaptive algorithms he had developed were automatically adjusting system parameters to compensate for electromagnetic variations, maintaining processing efficiency even as external interference fluctuated wildly. "Software performance is actually improving under stress conditions," he reported with obvious amazement. "The adaptive systems are learning from the electromagnetic environment and optimizing themselves in real time." But the ultimate test came when an unexpected crisis emerged during the demonstration's climax. Aircraft 773, while executing a high-speed banking maneuver during the formation flight, suffered a catastrophic failure of its primary flight control computer. "Mayday, mayday," came the pilot's voice over the radio. 773 has lost primary flight controls, attempting to engage backup systems. In the observation facility, alarm bells began sounding as tracking displays showed the aircraft deviating from its planned flight path. Without primary flight controls, the Lightning II-X was essentially a $50 million projectile, following ballistic trajectory toward the ground. "Backup flight control systems are not responding," the pilot reported, his voice professionally calm despite the life-threatening emergency. "Aircraft is not responding to control inputs." Dr. Hawthorne turned to her technical team with obvious desperation. "What's the status of backup systems? Why aren't they engaging automatically?" "Unknown," replied the lead systems engineer. "Diagnostic telemetry shows backup computers are functional, but they're not taking control of flight surfaces." Zara studied her electromagnetic monitoring displays with growing understanding. While the primary flight control failure appeared to be a random system crash, her instruments were detecting electromagnetic interference patterns that suggested a more complex problem. "Dr. Hawthorne," she called out urgently, "the electromagnetic readings suggest that the flight control failure triggered a resonance cascade in the backup systems. They're functional but can't communicate with the aircraft's control surfaces because of electromagnetic interference." "That's impossible," the systems engineer protested. "The backup systems are completely isolated from the primary computers. Electromagnetic interference can't affect both simultaneously." "It can if the interference is resonating through the aircraft structure itself," Zara replied, her mind racing through the electromagnetic pathways she had mapped months earlier. "The primary system failure created an electromagnetic surge that's being amplified by the aircraft's metal structure." Bradley looked up from his diagnostic displays with sudden comprehension. "The software isolation protocols are working perfectly, but they can't overcome electromagnetic interference that's affecting the physical connections between computers and control surfaces." In the air, aircraft 773 continued its uncontrolled descent while international observers watched in horror. The pilot had perhaps 3 minutes before the aircraft would impact the ground, taking with it not just a human life and $50 million in hardware, but potentially the entire Lightning II-X program. "Can we guide him through manual overrides?" General Morrison asked. "Negative," replied the test director. "Modern fighters are too complex for manual flight control. Without computer assistance, the aircraft is unflyable." Zara made a decision that surprised everyone, including herself. "I need direct radio contact with the pilot," she announced. "Specialist Thorne," Dr. Hawthorne protested. "This is not the time for experimental procedures." "Dr. Hawthorne, the pilot is going to die unless we eliminate the electromagnetic interference that's preventing his backup systems from engaging. I know how to do that, but I need to talk him through a manual procedure." General Morrison studied Zara with the calculating gaze of someone making life or death decisions under pressure. "Give her radio contact," she ordered. 773, this is ground control. Zara spoke into the radio microphone with steady authority. "I need you to access the aft electronics bay and manually disconnect the primary grounding harness." "Ground control. I can't leave the controls during an uncontrolled descent," the pilot replied. "The aircraft is already uncontrolled," Zara responded. "Disconnecting the grounding harness will interrupt the electromagnetic interference and allow your backup systems to engage. It's your only chance." For a moment that felt like an eternity, the radio remained silent except for the sound of wind rushing past the diving aircraft. Then the pilot's voice returned, tight with concentration. "Moving to access aft electronics bay. This better work ground control. Follow the main grounding cable to where it connects to the structural beam," Zara instructed, visualizing the aircraft's interior from her months of electromagnetic mapping. "You'll see a large connector with a red safety cover." "Found it," the pilot reported. "Removing safety cover now." "Disconnect the grounding cable and the electromagnetic interference should stop immediately," Zara continued. "Your backup systems will engage automatically once the interference clears." In the observation facility, everyone watched tracking displays that showed aircraft 773 still diving toward the ground. If Zara's theory was wrong, the pilot would die, and the Lightning 2X program would end in catastrophic failure witnessed by defense officials from 12 nations. "Grounding cable disconnected," the pilot announced. Immediately, Zara's electromagnetic monitoring equipment registered a dramatic reduction in interference patterns. The resonance effects that had been preventing backup systems from communicating with flight control surfaces disappeared as the unintended electromagnetic pathway was interrupted. "Backup flight controls are engaging," the pilot reported, his voice filled with relief. "I have control authority returning. Aircraft is responding to inputs." On the tracking displays, aircraft 773's dive began to flatten as the pilot regained control and initiated recovery procedures. The crisis that had threatened to destroy the entire program was ending as the fighter climbed back to safe altitude. 773 is returning to controlled flight, the test director announced, all systems showing normal operation on backup computers. The observation facility erupted in applause as international delegates realized they had witnessed not just a successful test, but a dramatic demonstration of crisis management under the most challenging conditions imaginable. Air Marshal Thompson approached Zara with obvious respect. "Specialist Thorne, how did you know that disconnecting the grounding harness would restore flight controls?" "The electromagnetic interference was using the aircraft's structure as an antenna," Zara explained. "When the primary flight computer failed, it created an electromagnetic surge that resonated through the grounding system and prevented backup computers from communicating with control surfaces." Defense Minister Richter studied her worn toolkit with new appreciation. "And you diagnosed this problem using equipment that appears to be decades old." "Sir, the age of the tools doesn't matter if they can detect problems that newer equipment." "Mrs. Zara replied, "My grandfather's instruments were designed to find electromagnetic anomalies that don't appear in conventional frequency ranges." General Morrison addressed the assembled delegates with obvious pride. "Ladies and gentlemen, what you've witnessed today demonstrates not just the Lightning 2X's capabilities, but the innovative problem-solving approaches that made those capabilities possible. She gestured towards Zara, Bradley, and Rebecca. This team combined traditional investigative techniques with cutting-edge technology to solve problems that conventional approaches couldn't address. Their methods are already influencing aircraft design and maintenance procedures worldwide. As the demonstration concluded and international delegates began discussing procurement contracts, Zara found herself reflecting on the journey that had brought her from dismissed support staff to essential team member. The woman who had been mocked for her rusty tools and outdated methods had just saved a pilot's life and a multi-billion-dollar program using the same supposedly obsolete equipment. Dr. Hawthorne approached with a proposal that would change everything once again. Specialist Thorne, the success of today's demonstration has convinced our board of directors to establish a new department focused on integrated system solutions. We'd like you to head that department. Mom? Zara asked, not quite believing what she was hearing. We want you to lead a team that combines traditional mechanical expertise with advanced technological approaches, Dr. Hawthorne explained. Your methods have proven that the most sophisticated problems sometimes require the simplest solutions, and the oldest tools can reveal information that the newest computers miss. Bradley and Rebecca approached with obvious excitement. Does this mean we'd be working together permanently? Bradley asked. Exactly, Dr. Hawthorne confirmed. The three of you have developed complementary approaches that achieve results none could accomplish individually. We want to institutionalize that collaboration and apply it to next-generation aircraft development. Indeed, as the sun set over Edwards Air Force Base, Zara packed her grandfather's tools for the final time as a maintenance specialist. Tomorrow, she would begin work as the Director of Integrated System Solutions, leading a team that would influence aircraft design for decades to come. The journey from rejected candidate to program leader had taught her that success often came not from conforming to expectations, but from maintaining the courage to approach problems differently. In a world obsessed with the latest technology, there would always be value in understanding how things really worked at the most fundamental level. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.